All right, good morning. The streaming is on already, so I can close that particular browser. And this is what this is what I'm planning to talk about today. Let's see, we still got some time before the class starts. Yep, still got about 3 minutes. So if you guys have any questions, you can kind of line up those questions, and I will attempt to answer those questions during the class. And I need to do something because my screen is off just a little bit. Final review on Tuesday. Well, let's check out when we're gonna have our final exam first. Yeah, probably. I'm just gonna double check because we actually worked it out last time too. So we'll take a quick look here. Yep, so it's December 14th from 8 to 10 a.m. Okay. Well, the only reason why I'm kind of hesitating to give you guys a final exam review, well, there are two reasons. One is I don't want someone to hold me to the practice exam and ask how come my final exam does not look like the practice final exam. So I'm going to have a disclaimer when I talk about the practice exam, because I'm just going to give you guys what we had last semester. There's no promise, there's no obligation whatsoever that your exam is going to resemble that particular exam. So that's the first thing. First reason. The second reason is I think we might have one more class before the final exam week. So okay, let's take a look here. Okay, so the exams are starting on the 10th, and I think the 9th we still have classes. So that means we have one extra class after next Tuesday, if I read this correctly. Is that correct? Can anyone confirm whether we have class next Thursday or not? Okay. Yeah, so we're going to have class on the 9th. But since I want to talk about the exam 1 week prior to the actual exam, so that makes it next Tuesday. So Richard is correct. Next Tuesday would be the right time to talk about the practice exam for the final exam. But we also have the Thursday after next Tuesday for classes. So I can use that one extra class to clarify some additional concepts. So I think that probably is what I'm going to do. Is that, which also means we have enough time for one more homework assignment, because I can disclose the key to that homework assignment next Thursday, and you will still have time to utilize the key to that homework assignment to prepare for the final exam. The final exam is not going to be okay, I'll put it this way. You cannot look at the final exam as a non-comprehensive final exam, because we still have to use the flags, right? We still have to use the correct flag for comparison. So that means you still have to understand the differences between the borrow flag versus the L flag, and how the L flag is derived, when to use it, and so on. You still have to understand the instructions. So, what is LD, what is LDI, what is CPR, how are those, three instructions different? Those are still important. So I cannot really say it is non-comprehensive. It's just that I'm not going to ask specific questions about the sign flag. I'm not going to ask specific questions about the overflow flag, and I'm not going to ask specific questions about how things are arranged in the processor in order to get something done. So I think that probably is the best way to answer Hamza's question. Is it is not going to be comprehensive in the sense that you will have specific questions about all the material in this class, but at the same time, it also does not mean that material that we have material in exam 1 and exam 2 will not be useful in the final exam. So a lot of the material from exam 1 and exam 2 will still be applicable in the final exam. It's just that there won't be any specific questions about those things. It's kind of be assumed. Yeah, I'll try to get the labs done, graded. But for the most part, I probably have given you the solutions. So if there's a lab where I have not given you the solution, let me know and I'll go over all the solutions. Because I think it is important for you to see the solution. Otherwise, you won't know what the correct answer is. So I think it's important for me to get that out first before, before I do the actual grading. So Daria, if you want to, just let me know if there's any homework assignment where the key or the answer is not disclosed. Let me know, and I will, post the answers and explain the answers first. So there's that. All right. So we don't really have a whole lot of time to spend, so I'm going to get started right away. So this is my job for today. It starts off with some screenshots of CISP310 because I want to emphasize that you are supposed to have learned how to use structured data, otherwise known as structs, in CISP310. So these are topics. This is the course description, and within the course description you can see how arrays, pointers, structures, classes, and objects are a part of CISP310. And then these things over here are topics. We can see how structured data is here. Pointers to structures is also here. And then down here we have, let's see, there's one thing, member access. There we go. How do we access a member in an object of a certain class? So those things are somewhat assumed. Now, if you guys need a kind of like a quick, review of those things, I can certainly do that. But otherwise, this is what we're going to talk about today: is how do we do structs in assembly language. And Matt is typing something. I'm going to keep an eye on the text channel. Oh, there we go. I personally was not taught class or struct until CISP400 this semester. That is unfortunate. Unfortunate at the same time because now you do know, structs and classes. So, so I can talk about structs a little bit. Okay, so let's go ahead and talk about structs. So the example is, okay, yeah, I don't like how the markdown side and the actual rendering is not fully synchronized, but that's because there's a difference of length here. I understand that, Matty, but it's supposed to be in CISP310. So I'm not going to assume that people have taken CISP400, but I can assume that this is taught in CISP310. If not, well, I'm not sure what to do with that situation. I really don't know what I'm supposed to do with this situation. Okay, this is a CISP310 is a prerequisite of this class for very important reasons. And so if someone is not teaching structures in CISP310, all right, so I would try my best to explain it, and not to take up too much time, because the objective of this class is to have the assumption that you already understand structures, and we are just going to do structures in assembly language. So there you go. Yeah, so okay. All right. Yeah, so I'm going to move forward with a very quick review of structures. But I cannot, ignore this topic because it is a very important topic. All right. So pointers and structures are two orthogonal concepts. So you can learn about structures and then you can learn about pointers and then combine those two because those two are basically orthogonal concepts, which means they are independent. Even though they can stack up, they can be combined, they are independent concepts. All right. So let's go ahead and start with this definition over here. So let me point out where we are at this point. So this is a struct definition. And what it is doing is it is defining uppercase X as a structure, which is kind of like a class, but it is it's a lesser version of a class. Okay, you can kind of look at it that way. It is a lesser version of a class where all the members are by default public, and also you cannot have member functions within uppercase X in this case. So we got three members. First member is X, second member is Y, and then the third member is Z. So these are called members of a struct X, being components of this particular structure here. So struct X is not defining an instance of a structure. It is actually defining a template for a structure. This is a cookie cutter. We are not cutting cookies just yet. We are just creating a cookie cutter. Sort of, Jonathan's question is actually correct. That would be a good assumption of what I want this class to be about, is to look at CISP310 and be able to convert most of the things into assembly language. In other words, you're gaining a X-ray vision into your C++ programs. All right, so. And I'm not sure why online GDB is showing up on a different window, but there we go. So all I want to do here is to show you the syntax. Okay, so we have struct X, and I'm going to keep the same definitions. So we have uint 8 underscore tx lowercase, uint 8 underscore ty, and this one is an array of 4 items. And uint 8 underscore tz, which is a single 8-bit unsigned integers. And then we have pound include stdint, standard integer.h. So this, from line 12 to line 17, we are not defining a variable. We are defining the structure of variables of this particular type, which is struct X in this case. So the easiest way to create a variable in this case is to use struct X as a type. Just like int, just like unsigned, it is a type. So we have struct X as a type. And now we can say, oh, let's go ahead and create a variable called var1, which is of the type of struct X. So once we have the variable of this particular type, then we can try to access members of var1. So we got var1.x, being the first member, and now we can say, well, let's put 2 as a value into that particular member of var1. And then for var2, for var1.y, it is an array, so we cannot just do something like this. This is not going to work because y is an array. Y as a member of var1 is an array, so we can do indexing, right? So we can do something like that. And then for z, it is just another 8-bit integer, so we can just have a regular assignment statement, something like that would work. Okay, I heard a few things going on. Is anyone else behind from the audio? Okay. Yeah, try to use Discord itself, when you are in synchronous mode, because I think Discord itself has a much more reasonable lag time. Okay. So now we can get rid of the printf because it really is not needed to do the demonstration here. And then we put a breakpoint over here. specify this is a C program, and then we go ahead and debug the program. All right, so now we are gonna run the program. So R, run the program, and now we're at the breakpoint, which is right before the subroutine returns. And right here we can see all the members of a var1. Member X has a value of 2 right here because we assigned a value of 2. Y, on the other hand, has a bunch of stuff because it is an array of 4 chars, but the first one at index 0 is indeed 4 because that's what we put into the first element in the array Y as a member of var1, and then Z has a value of 5 because that's what we put into Z. All right, and then we got some questions in the text channel. When arrays are allocated, all values of the arrays are initially 0. That is not true. So just like any other local variables, this line on line 21, all it is doing is to reserve the stack space for local variable var1, but it is uninitialized. So it would just take whatever content is in those bytes on the stack at the time of the allocation, and that's it. So var1 was uninitialized on line 21, and line 22 is the beginning of the initialization of the various members of var1. So all the bytes, okay, not just Y, but all the bytes that belong to var1, they're all uninitialized. They're basically leftover content on the stack because of some prior operations. Next question. It's just reserved space until something is specified. Yes, so Matt is correct about that. Okay, cool. All right. So now, now that we have a basic understanding of structures, and by the way, the double precision floating point number homework assignments, those utilized structures. So you have been exposed to structures already. Otherwise, you would not have been able to do that specific homework assignment. So there you go. So, yep. So yes, so we do have exposure to structures in this class already because of that homework assignment. All right, so now the concept is, how do we do this in assembly language? And we can just kind of focus on the program that we have right here at this point and focus on, okay, how do we translate this into assembly code? So let's go ahead and kind of reason this out and find out, how we can do that. And to do that, I am going to use one of my terminals, like this one, and then we'll push it to, oh, okay, actually it does show enough space here. I just want to position things to the point where we can see both the C code and the assembly code. And we'll call this struct.ttpasm. All right, so the first question is, how do we define a structure in assembly language? Well, the answer is you cannot. Okay, in a certain sense, you cannot, because there's no such thing as a structure in assembly language. But it does not mean that we cannot represent what kind of information we need in order to utilize a structure. So the way we do this is we take a look at a struct X thing and we ask the question, where do we find all of these members inside the struct X thing? So I'm going to put this into comment, into the comment area, and we want to look at what a struct X thing is going to look like. So as the usual thing, I am going to visualize how things are organized. So at the lowest level, okay, a struct X thing has a member X, and that's going to take up 1 byte. And then the next thing on top of that is going to be Y, but Y is going to take up 4 bytes because Y is an array of 4 bytes. So Y bracket 0, Y bracket 1, Y bracket 2, and then finally we have Y bracket 3, sorry, there we go. So now we have all the members of Y as an array, and then Z is really just right after that. In other words, a struct X is a contiguous region of memory inside your memory space. It can be static, it can also be a part of the stack, depending on whether we're dealing with a global variable, a static local variable, or we're dealing with an auto local variable. But this is what it looks like inside the struct X. Okay, at the same address as the struct X itself is where we can find member X. The next thing is going to be member Y, and then 4 bytes after that we can find member Z. I'm looking at the text channel. Variable X of X is at the top of the stack. Nope, we are not. This is not the stack. Okay, so what you're seeing in the terminal is not really the stack. It is internally how a struct X thing is organized. It is broken up into 3 parts. We have member X starting at the same address as the struct X itself. We have member Y. It's not variable Y, by the way. It is called member Y, which is a part of a struct X. So member Y starts 1 byte after the beginning of a struct X, and then member Z starts at let's see, 0, 1, 2, 3, 4, 5. So it starts at offset 5 from the beginning of a struct X. So let me just add the displacement. This is at displacement 0. This is at displacement 1, 2, 3, 4, and this is at displacement 5 from the beginning of a struct X. Is that okay so far? I'm just talking about, once you have a struct X thing, okay, how are the members organized within a struct X? So given this is how we can look at a struct X, we can use a bunch of label definitions to capture the same kind of information. So the convention that I usually use is to use the name of the structure, which is usually in uppercase, followed by an underscore, and then followed by whatever I want to say about the structure. So in this case, we have uppercase X as the name of the structure, lowercase x as the member of the structure, and it is at an offset of 0 from the beginning of a struct X. That's why it is defined as 0. What about Y? Well, you can always say Y is 1, but that's not how I would like to do it, because I want to refer to member Y, or the offset to member Y, as where member X is located and adding to it the size of member X, lowercase x. And member X is only 1 byte long, and that's why we have this 1 over here. What about member Z? Well, member Z is relative to member Y, and then we have to add to it the number of bytes that member Y is taking up, and that would be 4 bytes. And then there's one last thing, which is the size of an entire structure. So in this case, it would be the last member of the entire structure plus the size of that last member. So in this case, x underscore size is going to be 6, because each struct X thing is going to take up 6 bytes wherever you want to allocate it. So I'm going to take a pause here and see if there are any questions about how we are quote-unquote defining the structure itself, even without a language feature to do it. Where would this be defined? You can define it anywhere, because in assembly language, the convention is label definitions can be anywhere, because forward references are just as fine as backward references. So you can put this anywhere you want. You can even put it all the way at the bottom of your entire program. It doesn't really matter. And Matty is typing something. I'm gonna wait a little bit there. And then meanwhile, okay, so for x underscore y, x underscore I'm not sure what Nicholas is referring to. Y as a member is taking up 4 bytes. So because Y is an array of 4 unsigned 8-bit integers, and that's why it's taking up 4 bytes. So Y alone as a member is taking up 4 bytes. X takes up 1 byte, and then Z also takes up 1 byte. So the entire structure, uppercase X, is going to take up 6 bytes. X underscore Y is not 4 bytes away from the offset of X. It is just 1 byte away because it's right next to it. So if you are looking at where y is located relative to the beginning of the entire structure, it is only 1 byte away from the very beginning of the entire structure. All right. Any other questions? All right. Yeah, so this picture is really important. So every time you're dealing with a struct definition or class definition, because a class is really a glorified structure, every time you look at a struct definition, you definitely want to draw a picture of how the members are organized in memory. Which one is after which one and how many bytes each one is taking up. All right. Any other? Oh, okay. Then we do have another question coming, so I'm gonna wait for that. And when I'm waiting for that, I am going to use the usual thing. Okay, so we have no op jmpi to main, and then main is over here. This time we don't have any actual subroutine, so the jmpi to main is really unnecessary. Okay, but it's not wrong either, so I'm just going to keep it like that. We initialize the stack pointer. I thought that was another question coming, and it never shows up in the text channel. All right, so now we have main. So main starts with subdd to initialize our stack pointer, and it ends with a halt because, well, guess what? Main is not really a function. There's no place for it to return to. So the first thing we need to do in main is to look at this and go like, main needs to have a local variable called var1. How are we going to do that? Well, the allocation of a local variable does not change. Okay, the mechanism of allocating a local variable does not change, whether it is an integer, whether it's an array, or whether it is a structure. It is still allocated from the stack. Okay, so in this case, we're going to have to say, okay, fine, how many bytes do we have to allocate from the stack in order to make space for our local variable var1 here. So I'm going to let you guys answer the question. How many bytes do we need to allocate from the stack in order to fit a variable of the type struct x, sorry. 6 bytes. All right, excellent. All right, so you guys are all correct. And I like Ivan's answer because it is it's a better way to utilize the labels, because that's the whole idea of using labels here. But the other answers are also correct, given the way we define struct x in this specific case. So what we're going to do is to do an LDI. Okay, register A is fine, x underscore size, and then we do a subtraction. Okay, so we are subtracting sub. We're subtracting A from D in order to allocate for the space for our local variable var1. But that also means in order to balance the stack, we also have to remember to do the opposite when we are done at the end of this particular quote-unquote subroutine. It's not exactly a subroutine, but I still want to keep things balanced. So at the very end, we are just going to add the same amount to the stack pointer. So are we doing okay so far with this? Let me turn on the line number so I can refer to the line numbers. So at this point of this program, line 18 and 19, they are here to allocate the space for local variable var1. And since var1 is not a simple thing, it is a structure, it's okay. It's not a big deal. We just have to figure out how many bytes a struct x needs, and then we just allocate that much on the stack. Lines 21 and 22, they are the opposite, okay, of the allocation. They are the deallocation. So every time we allocate something on the stack, you better make sure that somebody is going to deallocate it also. Oh, you plug this into the assembler. I hope you're not plugging your headset into the assembler, because that may not work. What happens with the labels? They're simply defined. Okay, so if you look at the labels, x underscore x is just defined to be 0. X underscore y is going to resolve to 1. X underscore z is going to resolve to 5, and then x underscore size is going to resolve to 6. No, they don't do anything in the assembler because labels are really just symbolic names for numerical values. It is an easier way for us so that we don't have to keep on referring to the literal constant of 6 over here, and instead we can just rely on a symbolic name, which is easier for people to utilize, because otherwise you have to remember all the time, like, what is the size of a struct X, and whenever we change the definition of a struct X, you're going to have to change all those 6 references to something else. So that's just a convenience feature. Now, it does do something to the assembler. Okay, so let me just kind of exit the program and have it assembled. So that's a good idea, Maddie, to basically just see what happens when we have a program like this. All right, so I'm gonna assemble this program, and there are a few things you can actually observe from the assembler. It doesn't run. Okay, there's nothing it would do that is actually significant. However, okay, let me find my assembler. I have so many tabs open. I found this little extension to be quite useful because it allows me to locate a tab from somewhere from one of the windows and quickly. So there we go. So the thing we want to look at here is from the assembler's perspective. These labels are not, the definition of the labels are not shown up here, but they do show up when you look at Sim tab. So if you go to the Sim tab tab, okay, so Sim tab seems like a stupid name, okay, because why would you name a tab? Well, the tab in Sim tab is not tab, it is actually the abbreviated form of table. So Sim tab is actually symbol table. This is a fairly common abbreviation people use in compilers. Okay, so when you start to write compilers, you need to keep track of what we call a symbol table. So SymTab is actually a term that I borrowed from writing compilers. But once you get here, you can see how XX is defined to be 0. So the RPN is the actual value of whatever label that it belongs to, and then XY is right here. It is defined to be 1, and then we have XZ here, which is defined to be 5, and last we have X underscore Z, which is defined to be, where is it? RPN is 6 right here because it wrapped around. And main is, as a label, is also defined. It is defined to be 3, which is location 3 in this case. So so I hope this kind of shows Matty, how the label definitions are actually doing something. Now we haven't really started. Well, we actually did utilize one of the labels. We utilized X underscore size of this program up to this point, but the labels are already defined in the symbol table, and you can check that. Now, if you find this to be really hard to read, you can use a JSON, JSON beautifier, beautifier. There we go. And there are many of these things that are existing, so you just kind of paste the JSON representation. And okay, how does it work? There we go. So you can now actually check out the RPN value of each one. You can also go to a tree view beautify. There we go. Okay, so this makes it easier for you to visualize how the labels are defined. You just have to go to a JSON JSON beautifier and then copy and paste the cell from SymTab over to the text area, and then I would just use beautify, because otherwise it collapses everything, and it's just more work to work it out. All right. Alrighty. It's okay. Rabbit hole is my specialty. There we go. No, this is not unnecessary. I think it's a good idea to kind of utilize everything that is maintained by the assembler to give you an insight of what the assembler is actually trying to do, and the value of the labels in this case as well. So it's all good. Oh, okay, I forgot about that question. Yes, RPN is reversed Polish notation. it is made, I would say, famous, or at least known to people by HP calculators. Earlier HP calculators, they all use RPN to enter expressions. So I know you guys all have TI calculators that can handle all the infix notation, but long before your days, okay, back when I was a freshman in college, HP calculators were the only scientific calculators that people would use. So they all use RPN, which is reversed Polish notation, and our assembler makes use of RPN when you define the label, or you can just use RPN to define any expression for an immediate value. So it's kind of cool that way. Alright, so I am starting to lose track of what I'm supposed to do, but that's okay, I still got it. And let's see, for the browser, I need to go back to my online GDB tab. Alright, let's find online GDB. Online GDB, there we go. There we go. Alright, so getting back to here and also our assembly code implementation. So we are getting back to the implementation. Alright, so far what we have here is the beginning of main and also the end of main. Now, it is a good idea, I think, to define a label for var1 just as the usual thing, right? We define a label that becomes the offset from where the stack pointer points to that thing that we want to refer to. So in this case, var1 as a label, which is the offset from where the stack pointer points to the first byte of var1 as a local variable, is simply 0 because we don't have any other local variables in this particular program. So by the time the stack has allocated the space for var1, the stack pointer itself is going to be pointing to var1 itself. Alright, so now what do we do with line 22 of the C code? The first part is easy. The right hand side is just a constant of 2, so that's pretty easy to do. LDI A2, that handles the right hand side of line 22 of the C code, which coincidentally is also line 22 of the assembly code. Now we need to work out the left hand side. In other words, where is member X of var1? Now, some of you, okay, if you have been following where the stack pointer is pointing to and how we allocate the space on the stack and how the structure itself is arranged, some of you are going to say, Tech, we can just do this now. And you would not be wrong, okay? Very good, okay? You will be right that we can just do this. That is because we have only one single local variable in this case, and var1 is the only local variable. So the stack pointer is naturally pointing to var1 already. And on top of that, X being the first member of a struct X also means X is located at the very beginning of the structure itself, which also means where the stack pointer is pointing to is member X of var1 already. So that would be correct, but I don't want to do it this way. I don't want to do it this way because it relies on the fact that var1 is the only local variable and member X is the first member of the entire structure. So that would not be good, is because you cannot generalize this approach of doing things. So I want to give you guys the approach where you can generalize it. You can just go like, okay, as long as I have the offset of the members, as long as I have the offset to the local variable, this method will always work. Okay, so I want to give you that particular method. So the first thing we need to do is to figure out where is var1 itself, okay, as a structure. Okay, I don't care about the fact that var1 is a structure. I just want to know where it is as a variable. So that we have seen a lot of times already, right? Because we just load the label var1 into a register. I cannot use register A because register A is representing the right hand side. And then we add BD, which is adding D to B, so that now B is the address of var1. So now what do? Well, we say we have the address of the entire structure in B at this point, but we don't want the address of the entire structure. We want the address of a specific member of the structure. So that's what we're going to do next, is to say, okay, let's put the offset to the member, which is x underscore x, into another register C in this case, and then we say add BC. So at this point on line 26 of the assembly code, register B will now contain the address of the member x of the local variable var1, which is of type struct x. Whew, okay, that is kind of a mouthful, but let's pause here and see if everybody is understanding what we have at this point. Okay, no, okay. All right, so for the no, which part where are we losing the tracking of the variables, the registers? Okay, so LDI is load immediate. Whatever is the second operand, which is var1 in this case, is copied to the register, in this case register B. All right, so so that means in this case the B is offset to var1 from where register D points to. Is that okay? Because that's what var1 is as a label. That's how it's defined. No, D is not going to be 255 because we know that D is 0 here, and then we subtract 6 from D. So D is definitely not 255. It is going to be, what? No, you're close. You're close. What is 256 minus 6? Because 0 is 256 in modulo 256 math. 250, correct. So at this point, okay, after the sub DA on line 19, register D is going to be 250. So what we are doing here is var1 is 0. So we are essentially, just adding 250 to 0 and then store 250 into register B. No, var1 is not an address. var1 is a label. It is defined to be just 0. So as far as the assembler is concerned, every time it sees var1, it sees 0 as a value. And at this point, we are adding 250 to 0. And then after that, we are adding 0, which is in register C in this case, to 250, which also ends with 250. Yes, so Dalton is correct. var1 is an offset, and so is xx. var1 is an offset from where the stack pointer points to the beginning of a local variable. That's what var1 as a label is representing. X underscore x, on the other hand, is an offset from the beginning of a structure of struct x type to the member x, lowercase x, and that would be the meaning of x underscore x. So, yeah. So if we had a var2, it depends on how you want to order the local definition, the local variable definitions. So there's no right or wrong in this case. Okay, you can put var1 under var2. You can also put var2 under var1. So that convention is not determined by by the C++ programming language. So you can certainly do it in either direction. So there's no right or wrong, when you have multiple variables to decide which one is on top and which one is under. All right. You could do that. So if you have a var2, but that would not make a lot of sense in this case because var1 has a size of 6 bytes or x underscore size. So var1 1 plus would imply that var1 only takes up 1 byte on the stack. So you would definitely want to have x underscore size instead of a 1 when you want to compute the offset to var2. The way we allocate local variables has not changed since we talked about local variables. It's just that now we have a local variable that takes up multiple bytes. Yes, so Matty, that would be correct. Okay, if we want to define a second variable var2, then the starting point of var2 is going to be var1 x underscore size plus. Yep. Cool. Okay, very good. I like these questions. All right, so getting back to this program. Okay, so once again, I give you a little bit of commenting here, but once again, I want you guys to finish the commenting of the entire program. Okay, you'll go to every single line and comment what that line is actually trying to accomplish. All right, so finally, now we have register B being the actual address of member lowercase x of var1, which is of type struct x here. So now we can finally do the store. Okay, there we go. And now we have line 23, which really is boiling down to the same thing. Okay, so line 23 is LDIA with 4. And then we have LDI, whoops, LDI. This is why I like syntax highlighting, because as soon as I have a typo, I can detect it right away. And then we have add BD. So now register B is the address of the entire variable var1, but we don't want the entire thing. We just want member y. And since we are looking at the first element of member y, it is basically the same address as member y itself. So we can use the same approach as before. We load x underscore y into register C, and then we add BC, and now we can do a store to where register B is pointing to, which is the address of member y of the structure that we know as var1, and then the right hand side value is 4, which is stored in register A. So now that completes that particular thing, and I'm guessing you guys already know what to do with line 24 of the C code, but I'm going to do it anyway. Except I'm going to do it in a very lazy way. So line 30 to line 36, copy over here, and then we just change a few things, like that. And this time it's member Z, and then we store. Now I'm hoping you guys start to see why I want to maintain the offset to the various members as labels, because I can use. Oh, forgot one thing. That's the one thing that's kind of bad about copy, paste, and modify. If I forget to modify one of those things, it would still be syntactically correct, but then it would do the wrong thing. All right, there we go. Oh, okay. Okay, I think Matty spotted my error. There we go. Do you have to add all the offsets and the stack pointer before dereferencing? Or could you offset after dereferencing? Okay, so the question that Dalton suggested, it is best illustrated with a picture of what is on the stack. Okay, so I'm going to put it into this code here, and at the end of today's lecture, I can publish. I can send you guys all this particular program. All right, so let's check out what is on the stack. Okay, so what is on the stack, and I'm going to use one line per byte on the stack. So 1, 2, 3, 4, 5, 6. Okay, that would be sufficient. This is location 255. This is location 254, 253, 252. I should have used a spreadsheet, but then it will be a separate document. So using this way, I can put everything into this program. So this is just a picture of what is on the stack. Okay. So location 250 is kind of special because it is many things. Okay. First of all, this is where the stack pointer points to. Okay, because after the allocation, D is pointing to this location. I'm gonna line up everything. All right, so this is where the stack pointer points to. It is the beginning of the entire var1. Okay, so var1 starts here, but var1 stops here. as one single variable, this is what var1 is. var1 takes up 6 bytes on the stack, like so. But var1 is also a struct x, which means it has several members. Member x is right here. Member y of var1 is here. And then member z is all the way up here. Now, member y is an array, which means the first element is here. The second element is here. The third element is here. And then the last and fourth element is over here. Alright, so if you look at this picture here, and then we look at the definition of the labels. So the definition of the labels is var1 is simply defined to be 0 as a label. X underscore x is 0. X underscore y is 1. X underscore z is 5. And then finally x underscore size boils down to 6. So that's kind of the picture that we have here. Okay, the label definitions, they are all basically offsets with the exception of x underscore size. Every single one is an offset of some kind. It is relative to something else. var1 is relative to where the stack pointer points to, and since the stack pointer is pointing to var1 itself, it makes sense that the label var1 is a 0. X underscore x, y, and z, they are relative to the beginning of a struct x. Now, x being the first member of a struct x has an offset of 0. And that makes sense because the very first member of a structure shares the same address as the structure itself, the starting point of the entire structure itself. Y is 1 by the way, so that means it is at an offset of 1. And because y itself is taking up 4 bytes, so z is going to be 1 plus 4, which is 5 bytes away from the beginning of a struct x. The entire structure has 6 bytes because z itself is taking up 1 byte in this case. So I hope this helped to answer Dalton's question, not directly, but indirectly. Because you can now do the calculation and find out, okay, if I did it this way, what's going to happen, right? Okay, we got several questions coming in. So when those questions are coming in, I'm just going to end up specifying what the program is going to do. We're expecting a 2 over here. We're expecting a 4 over here. And we are also expecting a value of 5 over here. Because this is what we can do to check whether the program works or not. Okay, it's definitely helping with picturing the offset. Yep. Okay, so draw pictures, okay? But the picture can be deceiving because everything is only relative to where D is pointing to, which means, if you're in a subroutine somewhere, okay, especially when you have a recursive subroutine, you really cannot know, okay, ahead of time where the stack point is going to point to. But it doesn't matter. It really does not matter because everything is relative to where the stack point is pointing to at the time when this code is run. So that is kind of the beauty and also potentially confusing part of the call frame concept is everything is just relative to where the stack pointer points to. So, these values over here from 250 all the way to 255, it works only in this specific case. Okay, in other words, if main is calling a subroutine that has another local variable of the type struct x, then the offset would have changed. So I just want to point this out so that people do not get too stuck with, oh, okay, I need to know exactly the location of where the stack point is pointing to in order to work this out. The answer is no, you do not, because everything is relative to where the stack point is pointing to. So that is kind of the important point that I want to kind of emphasize. All right, so I'm going to wait for Matty's text, and once I have that, then we're going to test run the program and look at the trace and see if we can confirm whether the program is doing what it is supposed to do or not. All right. I think he just switched X and Z in the explanation. You mean me? what is he referring to, Maddie? Is it me or is it somebody else? Me. Tech. Okay. Why would I have switched X and Z? On which line of the code? 51 and 56? No, that is correct. Z is at a higher location than Z is, than X is. So I did not switch. That is actually correct. And then Jonathan has a question. I'm a bit confused why X is at the top of the stack. Isn't it defined first in the struct? But it has a lower address. So whatever is defined first as a member has a lower address compared to what comes after that particular member. So there's a particular ordering of the addresses of members inside the structure. Whatever appears first, so on line 14 of the C code, X being the first member means it has the lowest address of all the members. That's a convention. That's a convention used by most compilers. Let's see. The stack starts at location 256, which is 0. Yes. How does it know where to go to start the structure? Well, that's because we allocated the stack. That's why we did the subtraction to the stack pointer here. This is the allocation. This is how we allocated 6 bytes on the stack, which is exactly what we need in order to fit a struct X thing on it. And that struct X thing just has the name of var1. So the way we allocate memory for struct is opposite of local variables parameters. I'm not sure what you mean by that. It's still the same. Because the entire structure is one little chunk of thing, right? So when we allocate for the entire chunk. And then later on, when we need to address specific parts of that chunk, then we use the offset to the members of the structure to access each individual thing of the structure. Doesn't the first local variable go to a higher value in the stack? But that's the thing. Member X is not a variable. Member X is just a part of a struct X. It is not a local variable. X, Y, and Z as members, they are not variables. They are parts of a struct X. And in this case, var1 as a variable is of a type of struct X. And inside of var1, things are arranged in this particular order. So it's just standard we follow for the structs. Yes. And then Matty said that's kind of why I was asking when we define the variables. We do not have variables. We have a single variable var1 in main. So X, Y, and Z are not variables. On line 14 to line 16 of the C code, X, Y, and Z are called members of a structure. They are not variables. They are a part of a struct X. All right. I'm just waiting here to make sure that we have cleared all the text questions before we actually run the code to find out what it's going to do. Alrighty. So looks like, shall we move forward? I mean, do you guys need more time? I mean, I just want to know. Okay, yes to what? Moving forward or needing more time? Okay. Okay, so Matty, are we good to go or do we need more time? Yes to what? Okay, we're good. Okay, excellent. So I will give you this code, at the end of the class. You can also just kind of go to the assembler and make a snapshot of the assembler, because that will contain everything, right? It will contain the source code and also the trace of the execution of this program. So I would strongly suggest that you guys make a, don't do it yet, okay? Because I have not run it yet. But once I run it, you can go ahead and make a copy. Alrighty. So now we switch back to the assembler, and we go back to the other tab, to analysis. There we go. Alright, so in analysis, now we are looking for updates to the specific locations that I was illustrating earlier. Okay, so the locations that we should have changed is 250, which is in hexadecimal F what? Well, it's 6 less than a 100, so it's going to be a F0. Okay, so F0, F1, and FF are the locations that we should be expecting changes. So let's go ahead and check out whether that is happening or not. So we see FB, FF, and there should be one more. Oh, okay, I just scrolled a little too fast. FA. So I was wrong. It's not F0, it is FA, because A is 10. I forgot about that. So FA has a value of 2, FB has a value of 4, and then FF has a value of 5. So now we want to look at those and go back to the program, because I want to go back to the map that I had earlier here and double check and make sure that that is the case. Okay, so FF has a value of 5, FF is 255, so that does match. FB has a value of 4, so F4 FB is 200 and right, so FB is okay, FF is 255, so FD is 254, FC is 250. No, that's wrong. Okay, let me do it again. FF is 255, this is FE, FD, FC, and this is FB. 251 is FB, and it does have a value of 4 when the program runs, which is matching the expectation that we have here. And then when we scroll up in the browser just a little bit, we can see FA has a value of 02, and FA is right below FB, and in our picture here it is location 250, and it is supposed to have a value of 2, so everything does match up to what we were expecting the program to do. Alright, so now would be a good time to take a snapshot. So if you head out to, okay, I'm going to post the link right away so that you guys can get there with a single click. Easy peasy right there. Okay, so if you want to make a snapshot, because this is representing how a structure is going to be used, how we allocate for a structure, and how we refer to various members of a structure. Oh, missed the first click. Okay, not a problem. All right. I'm just looking at the time. We got about 20 minutes to go, so I think we can add a little bit more to this program, but I'm going to wait until you guys have a chance to take a snapshot first, and then we're going to move on. Well, actually I can move on in the C code first, and then you guys can continue to make a snapshot if you want to. I only got, what, 8 people on the spreadsheet right now, so the rest of you can head over and make a copy if you want to. But I am going to proceed with changing the program a little bit. I'm just gonna add a little bit more to the program. And let's see, where's my online GDB? Right here. There we go. All right. I'm just double checking my Discord and make sure that I'm not missing any questions. All right, so right here I'm going to define a function, and we'll call this function set. Let's call it set z, okay, instead of set x. So what it's going to do is it's going to take a pointer to a struct x. Okay, so ptr pointer is a pointer to a struct x, and all it's going to do, oh, we need another parameter which is value. So uint_t value. And all this is going to do is to update member z of the structure that pointer ptr is pointing to value. So it is ptr points to z, getting the value as a parameter. Okay, so we're gonna pause here and see if anyone has any questions about the new function that I have just defined in the C code. Are we doing okay on line 21? Now, line 21 is a shorthand, by the way, because there's another way to specify exactly the same thing, and it would look like this. Okay, we dereference PTR first. So because PTR is a pointer to a structure, so when you dereference PTR, it would be a structure. With any structure, you can access a specific member using the dot notation. So line 22 is actually exactly the same in terms of meaning as line 21. It's just that, for C and C++ programmers, line 21 is what most people would use as a notation to access a member of a structure that the pointer is pointing to. It is more or less I would call this eye candy. Okay, it's just basically eye candy. Line 21 is the eye candy version of line 22. But they both would get the job done just as well. I would say for beginners, line 22 is a slightly better way to look at things because now you can actually see the dereference. The dereference is explicit, whereas on line 21, it doesn't quite say that there's any actual dereferencing, and there's no explicit saying, and go like, oh, we are accessing a specific member, in this case, of the structure pointed to by PTR. So from the beginner's perspective, I like line 22 better, but the convention is people use line 21, once you're familiarized with how to use a pointer to a structure. All right, so I'm going to comment out line 22 because it really means it means the same thing as line 21. All right, so now we switch back to the assembly code. Okay, don't worry if you're still making a snapshot of the spreadsheet. I'm not changing the spreadsheet just yet because I need to implement this in the assembly code first, and then we'll go ahead and run it. All right, so now we have a new subroutine called setZ. Okay, so here's the entry point of setZ. It does not return anything, so that means I can easily just work out the exit code or the return code right away. So we're going to say LDAD increment D, and then we have a JMPA. So that's the end of setZ. But now we need to look at the stack. Okay, what does the stack look like at the entry point of setZ? So what is the caller putting onto the stack in this case? So we got value, we got PTR pointer, we got the return address. So at the entry point of the subroutine setZ, this is what we can expect. So in this case, I would define a label PTR to be 1 because it's 1 byte away from where the stack pointer points to, and I would define value as 2 because it is 2 bytes away from where the stack pointer points to. I know it's not consistent, but I would also prefix the entire thing with the name of the subroutine, just so that in case I'm going to reuse these names of the local variables somewhere else, there won't be any confusion. Yes, I forgot to do that with main. var1 of main does not have a prefix of main, so I forgot to do that earlier. I can fix that later. Okay. So are we good so far? Does everybody understand what these two labels are about? All right, cool. All right, so now the question is, okay, how many bytes is PTR taking up on the stack? Okay, let's address that question first. Okay, it really should not be a trick question, but I just want to point it out just in case there's any confusion. How many bytes is PTR taking up on the stack? 1 is correct. Very good. Okay, because it is a pointer. Now, but somebody may say, but it's not a pointer to a unsigned 8-bit integer like the swap subroutine. It doesn't matter. Every pointer only uses up 1 byte with an 8-bit architecture. So it doesn't matter what it is pointing to. The pointer itself is always just 1 byte long in this particular architecture. Okay, so I just want to point it out because it is really important that we understand a pointer is a pointer. Okay, it doesn't matter what it's pointing to. A pointer is always the same size, which in this case is 1 byte. Yes, the pointer is pointing to a location that can be interpreted as the beginning of a struct X, but it is also coincidentally the address of the first member of struct X, which is member X. Yes. And this is kind of interesting because in assembly language programming, there's no such thing as type, right? So it is just a location. Well, what is at that location? You can say it is the first byte of an entire structure, but you can also say it turns out to be, member X of that structure. Yeah, either way it's fine. There's no type information in assembly language programming. All right, so let's go ahead and work with this. So first thing is to retrieve value. So the retrieving of value as a parameter is something that we have done many times already at this point. So we load the offset first into register A, add AD so that we get to the address of the parameter, LDAA so that we actually get to the value of the parameter itself. So that is the right hand side. Now we work with the left hand side. So the left hand side is okay, so the first thing you need to do is to kind of find out what you're supposed to do. Okay, we need to find the address of member Z of the structure pointed to by PTR. Okay, that is what we need. So that means we need to start with PTR, right? Because we need to get to the pointer itself, then we can find the beginning of the entire structure. So that means we're going to do something that we are familiar with already. Okay, set Z underscore PTR, add BD, and this way we have the address of PTR. Is that what we want? No, we don't want the address of the parameter. We need to know what the parameter itself is pointing to. So that means we need an LDBB. So now we have register B is pointer itself. So at this point, okay, let me show the line numbers again. So on line 30, after line 30 is done, register B will be pointing to a structure of struct X, okay? It would be the address of the beginning of a struct X thing. But that's also not entirely what we want, because we want to go to a specific member of that structure. So now we have to load register C with the offset to the member that we want to access. In this case, it is Z. And then add BC here. Oh, that's LDI. See, this is why I like syntax highlighting, because it shows right away. It's like, tag, you just made a mistake there. There we go. Okay, so at this point on line 32, by the time line 32 is done, register B would then be the address of member Z of the structure that is pointed to by PTR. And that means we are now ready for the store instruction. So we have a store BA, okay, that will actually do the assignment. And we're done. Okay, the rest is just returning back to the caller. So I'm gonna pause here a little bit and see if you guys have any questions about the implementation of set Z as a subroutine. It is given a pointer to a structure. It is given the value that we want to overwrite that specific member Z of the structure that is pointed to by PTR, and then the implementation is, what we are looking here at on the screen. All right. There's some confusion on line 22 to line 24. Okay, so line 22 to line 24, that is something that we have used quite a bit, which is set z value is representing the offset, the number of bytes from where the stack pointer points to parameter value. So line 22 is loading A with the offset, but the offset itself is not very useful until you add the stack pointer to the offset. Then we have the address of parameter value, but we don't really want the value of we don't really want the address of parameter value. We want the value of parameter value, and that's why we need line 24 to do the dereference, because we are not interested in the address of a parameter. We want the actual value of the parameter. Oh, okay. Yeah, there's a second parameter right here. All right, next question. Okay, that's all good. And then Vlad is typing something. I'm gonna wait a little bit before I well, I'm going to wait, but at the same time, I am going to change main a little bit here. So instead of doing this, okay, on line 30, I'm going to change it so that we make a call to set z, and then we'll pass the address of R1 and also pass the value of 5 in order to do exactly the same thing as what we did on line 30, but this time it's going to be done by a subroutine. How does LDIC x underscore z still remembers what variable xz is? X underscore z is a label. It doesn't have a value. It is not a variable. It is not a value. It is a label. X underscore z as a label is representing the number of bytes from the beginning of a structure to member z of that structure. All right? So I can kind of see how, reviewing this video can be helpful, because I'm not going to lie, I mean, there's a lot of concept introduced in this particular module, but at the same time, these are pretty important things too. Yeah, so xz is a label. A label definition can never change. You cannot redefine a label. If you tried, the assembler would have complained. No, labels are, once you define a label, you cannot change the definition of a label. So label x underscore z will always be 5. Yes, so xz is the number of bytes from the beginning of a struct x to member z of that structure. Yep, okay. All right, so we're going to change these lines here. Okay, so we are going to get rid of the way that we did on line 30 of the C code, and instead we are going to call the subroutine now. So to call the subroutine, we push 5 first on the stack. So we load LDIA with 5, decrement D, STDA. Okay, so that's the second parameter. Now we need to put the first parameter on the stack, which is the address of var1. How do we do that? Well, we need to get to the offset first. Okay, so load A with var1, which is the offset from where the stack pointer points to local variable var1 of main. And we add AD, okay, so that register A is now the address of var1. Wait, hold on a second here. Hold on a second here, Tech. Are you telling me that register A after line 67 is exactly what we need? The answer is yes. Okay, so getting the address of something is actually easier than getting to the value of something. In C code, it looks like it is harder because you need a special operator of quote-unquote address of when you try to get to the address of something. But when you're trying to get to the value of something, you don't need anything. You don't need any operator. In assembly language, it is exactly the opposite, because you always have to get to the address of something first, then you can use dereferencing to get to the value of something. So we always get to the address of something first. So now we have the address of var1 in register A already. So we can do a decrement D, STDA, And then we can push the return address next, right? So LDIA with .6 plus, decrement D again, STDA, and we are ready to branch. Okay, I'm expecting someone to point out an error that I have in this code, so I'm still waiting because I intentionally made a mistake here. It's more like a neglecting something, okay, but the code as it is right now has a problem. So what is that problem? The problem is we have one extra byte sitting on the stack when we try to access something that is relative to where the stack pointer points to. Specifically on line 66. On line 66, we're trying to get to the address of var1, but lines 62 to line 64, specifically line 63, is decrementing the stack pointer by 1. So that means what we used to know about the offset from where the stack pointer points to var1 is off by 1 now, because we got an extra item on the stack. The stack pointer is now 1 less than what we thought it should be, when we defined the label var1. So Richard is correct. It is important that we remember that, there's one extra thing sitting on the stack now because we have to push the second parameter first, second argument first. So that's why we need to compensate for that one extra thing on the stack by adding 1 to what the label var1 is defining. So now we got everything, I think, and then obviously we need the 2 increment here because we have 2 arguments that would still be sitting on the stack when set z is coming back to main. So now the time is, we got about a minute to go, and I think we have just enough time to run it, assuming that I didn't make any stupid mistake somewhere. All right, so everything seems to run okay, and then we go back to the assembler. And it looks like the analysis is all done already too. Well, that was pretty quick. All right, so we can still see, so the bottom line is, are we still putting a 5 into the location of FF? Okay, so FF is supposed to get a content of 0.5. This is us pushing 5 as the second argument when we're calling set z. Oops, okay, there we go. This is pushing the address of the entire structure. This is the address of var1 that we are pushing on the stack when we called set z. I'm just going to use the keyboard to scroll here. And this is the return address when we called set z. So this is inside set z here, and inside set z we computed the address of member z of the structure that is pointed to by PTR, and then we store 5 into that location. So now I have just confirmed that we implemented the subroutine correctly, and then it went back to main, and then in main we incremented the stack pointer twice to get rid of the 2 arguments that were still sitting on the stack. And then we the 2 increments is here and also here. And then we also add 6 to the stack pointer because at the end of a subroutine we have to deallocate everything. So since we have the local variable var1 still sitting on the stack, we need to deallocate that. And to deallocate var1, which is a thing that occupies 6 bytes, we're just adding 6 to the stack pointer. And as a result, the stack pointer is now balanced. It is going back to location 0, 0, and the program concludes. So now would be a good time to take another snapshot of this program, because the way this program has at this point is not only does it demonstrate how we allocate the storage for a local variable that is a structure how to access individual members of a structure, but it also illustrates how we can access a member of a structure that is pointed to by a pointer. In other words, we have talked about all the concepts that we need to talk about already. So the rest is really just to apply all of these things in order for you guys to start to really kind of understand, what is going on, what C code is translating to what kind of code in assembly code. Now, the syntax of TTP-ASM is very specific to this architecture. It's definitely all me, but the approach of doing things is not. Okay, the approach of how we access members of a structure, how we access the member of a structure that is pointed to by a pointer, those are not specific. The approach is the same regardless of which compiler and also which architect with whatever architecture you're working with. So that's kind of the whole thing. And so I'm going to assign another homework assignment. So it's going to overlap with the current homework assignment, the Fibonacci homework assignment. Because it is important for you to get a chance to actually write the code in order to fully understand the concepts. Because it's the debugging process that is actually the most helpful. In other words, if I just give you the code and go like, this is the code that we implement that, it is just knowledge, okay? But until you actually get to do it and make mistakes and then understand, oh, if I make a mistake like this, the code is going to do that, and learn how to diagnose the program, that I think is the most important part of learning the concepts in this class. It is not so much understanding my code. It is not so much just reading my code and be able to understand what's going on. It is really going through the whole process. Having bugs is actually a great way to learn about the concepts. Now, I know it's counterintuitive, and I know how bugs can really frustrate a lot of people, but I think personally, I learn the most when I make bugs in the program. Go like, oh, I didn't know if I did something like this, the program would have done that. Why is it the case? So the moment you chase down why the effect of a bug is causing something to happen, that to me is a new level of understanding the concepts. So anyway, I will stop the lecture at this point. So I'm going to stop the screen share and also live stream, but I will also release. Yeah, go ahead.
I have a question if you don't mind, but I wanted to wait
Yeah.
till you were totally done.
Yeah, go ahead.
Okay. I have been tracing the LDI,
Mm-hmm.
add, and then LD
Mm-hmm.
instructions,
Mm-hmm.
and I want to make sure that what I think is happening, if
Mm-hmm.
I'm right.
Yeah, go ahead.
Okay. So LD takes up 2 bytes. Um, the first one tells the processor what register bank we're going to put the second bytes information into.
Okay, so
Is that right?
well, let's take a look at the opcode table. Okay, so for the rest of the class, if you think you're ready to go, you can go ahead and leave the session. But if you want to kind of review the opcodes, you can stay behind. All right, so this is the LD instruction. Um, and the comment of the LD instruction is x equals to the dereference of y. In other words, LDXY, now x can be one of the 4 registers A, B, C, or D, and y can also be one of the 4 registers A, B, C, or D. So x and y can both be A if we have a situation where that is what we need to do. But the idea is we are dereferencing register y. Whatever y is being used as the address. And we're getting to the location that y is pointing to. Grab the content at that location of RAM, and then use that content to update register X. Is that okay, Maddie?
Yes. That was I was originally talking about the LDI, but the LD is
Oh, okay. So,
also
okay.
what I was curious about. But that, so yeah, so basically, I
Mhm.
wrote a program that trying to emulate what we did on Tuesday,
Mhm.
and I had it assign two to register D,
Mhm.
and then I had it um, assign
You mean?
another number to
Mhm.
register A, and then add D to A.
Mhm.
And I saw it, yes, it increased the value in A by how much I put in D, which was two.
Mhm.
And then I had it do LD um, AD. So it then the pro it took what was in space two
Mhm.
of the RAM
Mhm.
and put the actual value for that in register A.
Yes. Yep. But you have to be careful because in most cases we don't want to load an immediate value into register D, in when we are dealing with subroutines. So as an entirely separated test program, register D has no special meaning. It is not a stack pointer, so we can do that. But when we are working with a regular program, where we are working with subroutines, when we need a stack, the stack pointer is register D, and you have to be very careful of how you modify the stack pointer, because the stack pointer is only used as a bookmark to separate which part of the stack is in use and which part of the stack is not in use. But I understand your example. So in your example, you're not using register D as a stack pointer, right? You're just using it as,
Correct.
as an arbitrary register. Yeah, so that would be fine. Yes.
All right, yeah, because I was trying to understand
Mm-hmm.
how when we do LDI
Mm-hmm.
that you say that the value that's in LDI is not the actual value we want, but the address.
Okay, so let me type this up a little bit. Yeah, just so that we have a written record of the discussion. So we have
Okay, yeah.
LDI, LD, and also CPR. Those three, each one will change a register. Okay, but the way it changes a register is different. So LDI A5 is really the same thing as, if you want to look at this, is really the same thing as A gets the value of 5. Register A has a value, it becomes the value of 5. That's what LDI is going to do. LDA, let's say register B in this case, boils down to A is getting whatever register B is pointing to in RAM. So I'm going to put these in a code block, so this way things look a little bit better. Okay, so are we good so far?
Yeah, would you
Yeah.
mind I was writing it, typing literally exactly what you just said after your comment
Mm-hmm.
that register A is
Mm-hmm.
getting what register B is pointing to in RAM,
Mm-hmm. Yep.
right?
That's what the
So
LD. Yeah,
so
that's the job of LD.
okay, so
Yep.
if register B
Uh huh.
um trying to like picture how that how that how that works. So we have the box of RAM, and
Mm-hmm.
let's say in space two.
Do you want me to?
Um,
Excuse me. Do you want me to pop up Logisim so I can actually point out the pathways?
yeah, because I'm trying to do
Okay.
that
Yeah.
and just
Sure.
going like, I don't know what to pay attention to while I'm
Okay.
doing that.
Gotcha. Okay. Let me do that. Yeah, these are very good questions. Because I think it's very important to understand the differentiation between LDI, LD, and CPR. And this is the kind of the most concise way to summarize what each instruction does, but it doesn't really show you what the pathways look like in the processor. So that's actually the whole purpose of me using my own processor in this class, is so that you guys can actually see what is going on inside the processor. All right, so it's coming right now. Okay, there we go. So I'm not going to actually run the code. Okay, so I will only go ahead and illustrate the paths. So let's go back to the first one. Okay, so we're going to look at LDI A5. So with LDI A5, what's going to happen is inside the register bank, register A will end up being enabled. Now, if you want register A to be enabled, you need its decoder to be on, so this needs to be a 1. And then you also need the input register select being 0, 0 in this case, so that we have a 1 going into the enable of register A. Is that okay?
Yes.
Okay, so that's part of what the ROM needs to do, is to kind of control all of these bits, so that register A is enabled, so it is ready to be changed. So the big question, so all three instructions that I mentioned, so all three here would do the same thing, because they all want to change register A. So the question is, how is the D port of register A connected when we have the rising edge? In other words, going back to Logisim, the question is, we know for sure that register in select is going to be 0, 0. We know in enable is going to be a 1. The question is, how is this particular pin connected in the processor? So we're going to go back to main. And what we are looking at here, so we want to know, how this wire is going to be connected. So we'll deal with it one step at a time. For the LDI instruction, it's going to be connected to the D port of RAM. So the D port of RAM is right here. So I'm going to highlight it like so. So now the question is, how do we route that to where we need it? Well, we're almost there, right? Because all we need to do is to configure this multiplexer in order to get to here. So that means RIMUX, register input multiplexer, as a control needs to be a 0, so that we are routing the D port of RAM into the input of the register bank. So that would be common to both LDI and also LD. So LDI, this 5 is actually stored as a separate byte compared to the opcode itself. It is right after the opcode. Because of the way we update or we post increment the program counter after we decode an opcode, so the program counter is actually already pointing to a byte with the content of 5 after we get to the ROM location corresponding to LDIA. So in that case, we also want the program counter to be connected to the A port of RAM. So the program counter is right here. This is the output, and we want this to eventually connect to this wire over here. So that means this multiplexer is playing an important part in that decision, and we want ADDR-MUX to be a 1 in this case, because PC, the program counter, is connected to input 1 of this multiplexer, and we want that input to connect to the output. So ADDR-MUX needs to be a 1 for the LDI instruction. So the LDI instruction is using the program counter to point to the location where a 5 is stored. Are we doing okay?
Yes.
Okay. But for LD, it's different, because for LD, we want register B to be connected to the A port of RAM. So in the processor architecture, that means with this multiplexer, we don't want input 1 to connect to the output anymore. This time we want input 0 to connect to the output. And we can see how input 0 of this multiplexer is coming from the demultiplexer coming out of out 1. So now we track down, so we need this select to be a 0, so that the only input of this demultiplexer connects to output 1 over here. So that means whatever is connected to the address port of RAM is coming out of out 1. So once again, we get into the register bank, And this time we want register B. So we want to connect register B's output to register out 1. So that means register out 1 select needs to be specifying 0, 1. So that's how LD itself is implemented. It's basically using one of the 4 registers inside the register bank to connect to the A port of RAM, so that that register, A, B, C, or D, is specifying which location we should be reading in RAM, but the other part is common, which is to update one of the 4 registers in the register bank. Are we okay so far?
Yeah, the part of what confuses me when I'm trying to like actually look at the code
Mm-hmm.
is just specifically going between RAM
Mm-hmm.
and the register bank. Since when we write code, that's mainly like, you know, what we're trying to figure out.
Mm-hmm.
Um,
Okay, so I can suggest a few sample programs to kind of illustrate the differences.
yeah,
So we can just write a program like LDI, register C, just put something random in it, like 17 in it. So after this code executes, you will find the register C ends up with a value of 17 because that's exactly what it is supposed to do. And then what you can also do now is to store something to location 17. So that would be stc, and then you pick another register. So we can put some specific value into register A. So we can say LDIA with I don't know, 31. Okay. So this would so basically I'm tracking what each instruction is doing. So A gets a value of 31 here, and what this one is doing is it is saying whatever C is pointing to is now getting the value of A. But we already know what register C has and what register A has. So in this very specific instance, we are basically storing to location 17 the value of 31. Now these are all in decimal, so when you look at it in hexadecimal, it'll be slightly different. And then we
okay,
can,
yeah.
yeah,
So
yeah,
ST is the only one that actually stores something in RAM, right?
yes,
That's
yep, that you are
that's
correct.
putting something on the stack, right?
Not only the stack is really just a region of RAM. So if you want to
Okay.
overwrite any location in RAM, you need the ST instruction. The ST instruction is the only
Okay.
thing that can change a
Yeah,
location of RAM.
because 17's not on the stack necessarily. Gotcha. Okay, yeah.
Okay.
Um, so
Mhm.
LD, or I guess go ahead because I'm
All right. So
loving this explanation.
okay. So let's try LD instruction here. So we can do LD to register B, C. Okay. So when we look at the what we call the RTL, the register transfer language, which is basically what column C of the opcode table is trying to do. What this is doing is B gets whatever C is pointing to. So in reality, we know what C is pointing to, right? Because we know C still has a value of 17. So we know we are dereferencing location 17 and grab whatever is there to register B. But we just stored 31 to location 17, right? So we know in this case 31 should be stored in register B as a result of the LD instruction. And then the last one is CPR, because I do want to emphasize that CPR um, is part of the family of instructions that can update a register. So CPR is much more direct. Okay, so in this case, now in this context, in this sample program, register D is not a stack pointer. Okay, so we can modify any way we want to because it is not being it's not assuming the role of a stack pointer. So we can now do something like this. Okay, so if you look up the opcode table, the opcode table says, oh, it really is just a simple assignment between 2 registers. Now that means we already know at this point register B ends up with a value of 31. So we basically say, oh, okay, so whatever register B has, which is 31, is going to be copied to register D. So register D would also end up with a value of 31. So let's go ahead and change all of these things to hexadecimal, just so, because otherwise it becomes kind of difficult to read in the trace. So this is 1 1, this is 1F. So everywhere you see 31 is 1F in hexadecimal. Everywhere you see 17 is 1 1 in hexadecimal. Is that okay?
Yes.
Okay. So now we can actually test run this code. Okay, so I am going to. I hope everybody has taken a snapshot of the earlier code because I'm going to change it now. Let me get out of Logisim. Do we want to look at Logisim, or is it okay not to look at Logisim? I can keep it up for a while. Okay, so I am going to make this new program. Okay, examples. Okay, ex.ttpasm, and here we go. Oop, nope. Let me see if I can do this. Control C and paste here. Nope, doesn't like that. Oh, that's not good. Okay, because it doesn't seem like I have an easy way to copy and paste from Joplin to my terminal. Okay, let me try one more time. Control C over here, and there we go. Okay, so that's good. And we want to edit it just in case I missed something there. TTPASM. Yep, there we go. And I'm still missing something. Missing what? The first instruction. LDIC17. And then we also need a no op because I want to trace this using the trace analyzer. So a no op needs to be the first instruction. And we also want to maintain the comment over here. There we go. Alright, so now we can test run this code. And as I said, I hope everybody has a chance to take a snapshot of the assembler because now it's going to change.
I got one.
Oh,
And can share.
okay. Alright, so now the program has just run and we need to go back to that browser and go back to the assembler. Where's the assembler? I got way too many tabs open. There we go. Alright, so it's just updating itself now. There we go. So we can now focus on just how the registers are getting updated, and we can also look at Joplin at the same time because in Joplin we have made all the comments. So we can see how the LDI instruction, the first one, is ending up putting a value of 1 1 in hexadecimal into register C. And the LDI instruction, the second one, is putting 31 into register A, which is in hexadecimal 1F. And then the ST instruction is putting the content, the value of 31, which is 1F, into location 1 1. And that is represented by this column over here. Column C is always representing what we are writing to RAM. And then the next one is an LD instruction. It ends up loading 1 7 into register B. And it's loading 1F into register B because 1 7 is the location, but at the location 17 is the value of 31, and 31 is 1F in hexadecimal, so it is correct. And then the last one is a CPR instruction. It copies whatever register B has, which is 31 in decimal or 1F in hexadecimal, into register D, and that's exactly what it did over here. I forgot a halt instruction, and that's why it just kind of went on and on and on.
Lol, but nice. Okay. Yeah, that's so helpful.
Yeah, yeah. So it's a good thing that you ask these questions because it is very important to understand what each instruction does before we start to kind of lump the instructions into larger units so that we can get more things done using these instructions.
Yeah, we'll all be talking, trying to like figure out what code is doing.
Mm-hmm.
And because none of us that are in our group feel like we have a really strong understanding,
Mm-hmm.
we're like, I think it does this. And we end up kind of spending a lot of time going, but wait, I thought it did that. Uh and
Right.
confusing ourselves. So having just this really straightforward clarification is great.
Mm-hmm. So this is one of the things where so there are several ways to approach this. The first one to approach this is to look at the actual code. So you go to the Assemble tab. Okay, you look at the actual opcode, which is in column X. So what you can do is to force feed that opcode into the assembly into TTP ASM. So in this case, you can basically force feed the opcode with a padding with a zero extra zero on the right hand side into the microcode pointer. So 6E0 for instance, I can just force it here. That will automatically point the ROM to the location where the content of that ROM location corresponds to the pathway that we want to investigate for opcode 6E. But what opcode 6E is really representing, okay, is the LDIC something instruction. So that's one way to, just kind of make the logic sim, to go to configure itself, as if it is actually executing a specific instruction. And once you do that, you can go back to the logic sim, and then now we can look at all the signals because all the signals are now configured the way that it's supposed to be configured in an LDIC something instruction. So now we can look into the register bank like so, and then we can see how the decoder is enabling register C, and then we also can track down what is connected to reg in. Okay, so we can see how this is enabling the multiplexer. We can also see how RI mux is a 0, which means the input 0 of this multiplexer connects to the output of the same multiplexer. So we now focus on the input 0 of the multiplexer, and now we can see how it connects to RAM right here. So the next question is, who is driving the address bus, right? The address port. So we track down the address port. It ends up with a multiplexer. This multiplexer has a select of 1, which means we are connecting input 1 to the output of the same multiplexer, and that is coming straight out of the program counter. So that's how we can use LogicSim to visualize. Now I know this is complex, okay? There's a lot of stuff here, but each component doesn't really do a lot of things that are very difficult to understand. It's not very abstract. It's how they work together that is important. So for the other example is if you want to understand how CPR works, okay? So now we can switch back to the assembler, look at the CPR opcode, which is 5D. So now we can force feed 5D into the microcode pointer. So 5D0 is what we need to force feed into the microcode pointer in this case. So we have 5D0. And now you can basically do exactly the same thing as last time to try to figure out what paths are established between the output of the register bank and the input of the register bank. Is that okay?
Yes.
Okay.
Um, I mean, to be like completely honest, when we talk about the inputs and the outputs and the register bank and stuff, a lot of that just really, I don't know, it really goes over my head, you know. But seeing how the register bank changes,
Mm-hmm.
and when RAM changes, and the PC, like those three components,
Mm-hmm.
um, seeing what they're doing,
Mm-hmm.
I find really helpful.
Well, I would say at this point of time, focusing on the macro effect of an instruction is more important than understanding the pathways. Now, I'm not saying understanding the pathways is not important, but at this point of time, just knowing what each instruction is accomplishing, not so much how it is accomplishing it, but what it is accomplishing, is probably more important. So, and to that end, one thing you can do, is to write more sample programs. I mean, really just write, 2 or 3 lines of code, run it through, either using the trace analyzer, or you can run it through the GUI mode of Logisim, and just look at the effect of those instructions and make sure that you can confirm that your understanding of what an instruction does matches the end result of running that program.
Okay, yeah. Yeah, I was trying to do that with LD last night and this morning. And I think part of the problem was what I had it like updating to
Hmm.
didn't make a change. And so I was like, what does this do? It doesn't seem to do anything. I didn't have the proper
Oh, okay.
um like set up
I see.
to make it get to do something. And so it's just making me more frustrated.
Okay,
But
so to that.
during your class today,
Mhm.
you made me realize that.
Okay, yeah. So to make your test code show the result a little bit more, you can always go into the register bank before you start to run your code, and actually go ahead and change the registers. So you can actually just click on a register, let's say register B here, and if you want to force feed like 7E into the content of register B, just overtype it, just overwrite it with 7E. So this way you can set up the program to have very specific values in certain registers, and you can do the same thing with RAM. So if you go to RAM, you have to be using the poking tool. This is the poking tool. So if you're using the poking tool, you can go to any specific location of RAM, like this one over here, which is 05, and you can just overwrite it and say, I want this RAM location to have a content of, let's say, D6. And so this way you can set up RAM and also the registers to a specific state before you test a very specific opcode to observe the outcome of executing that opcode.
Okay, yeah, good, good suggestion.
Yeah, I'm looking
All
at the
right.
I'm looking at the text channel. Someone is asking to go through all the programs in CISP360 and turn them into assembly code. The answer is no. um, we in this class, I don't want to write code that is tedious, but I do want to exercise all the key concepts, of combining pointers with structures and so on and so forth. So next Tuesday, we're going to go through the practice exam. And by the way, the practice exam has been published in, I cannot remember what day. I can do it again today. But it really is just a matter of a whole bunch of pointers, structures, and recursive function calls and whatnot. So we'll go over that on next Tuesday. All right. Um, any other questions, Maddie?
I think I'm good.
Okay. Yeah. So experimenting is very important, because by experimenting, you are not just asking for the answer itself. You're actually thinking about, how do I test what I think is what this instruction is going to do? How do I test it? So in the process of designing a test to confirm your understanding, that by itself is deepening your understanding of the concepts. If something doesn't work out, okay, if you say, okay, I am expecting this opcode to do blah, okay, but it ends up doing something else, not what I intended, that actually is a very good thing too, okay, because that means now you need to investigate what it actually ended up doing and where is the misunderstanding. That is a I'm just trying to look for the word here, okay. That is how I learn best, okay. I cannot say the same about other people, but this is how I learn best, is by experimentation. And I learn more when something does not happen the way it's supposed to, more so than when things happen as expected. So go ahead and
Oh, yeah.
yeah. So go ahead and experiment. I mean, that's kind of how we study for this class, okay? Because otherwise, there's not that, combined with the open source nature, like the processor is laid out, the way it is in Logisim. it's kind of how the material is delivered. But to understand the material, you kind of need to go through a lot of experimentation. Um, and when your code doesn't work, okay, you try to spend some time to think about why it is not working, what you expected to work, what actually happened. And if you cannot figure that out, you can always, just ping me. I'm not talking about just Matty. This is directed to the rest of the class as well. Is when it doesn't work, you can always ping me. But when you ping me, don't just tell me that my program is not working, because that is not very helpful to me. You kind of have to say, I was expecting this program to do blah by the time it gets to this line, but it's not doing that. And instead it's doing blah, blah, blah. And why is that? That is far more useful, to me, in order to give you guys pointers of, how to think about that situation from that point on. All right. Any other questions before I get off of screen share? All right.
I also have a question.
Yeah, go ahead.
Can you bring up the C program that you went over today and its assembly?
Yes. Hold on a second. I think I put that program into online GDB. And too many windows. Way too many. Alright, so here's the C code. And you would like to see the assembly code too, right?
Yes.
Okay, so give me a second here. Bring up the assembly code. There we go. And I can turn on line numbers, so you can direct me to which line you would like to look at.
Well, so this is my question.
Mm-hmm.
On online GDB,
Mm-hmm.
on line 29, you have you're assigning member Y its element 0 to 4.
Mm-hmm.
Suppose instead of 0, I wanted to do element 1.
Okay, very good.
So,
okay, fair enough.
And what I was trying to figure out is in TTP assembly,
Mm-hmm.
because I noticed that if you bring the assembly back up real quick.
Yeah. Oops.
So I'm trying to remember what line it was on.
It's let's see. It should be right before somewhere around here. I see the reference to Y here.
Yeah, there it is. So on that particular line,
Mm-hmm.
so suppose I wanted to, instead of assign element 0, it was element 1. I'm assuming what you would do is yeah, okay, I thought so. I just wanted to make sure. I was just like, wanted to make sure because I wasn't too sure. So it's like, is that correct? I'm not sure. I better ask.
Okay, since you go ahead. I'll let you finish and then I'll bring up something else. Go ahead.
Because of this, I'm kind of noticing, is this why in arrays the elements always start at 0 and then go to 1 and to 2?
Yes.
So that's where it comes from.
Yes, this is why it is 0 oriented, because the first element is exactly at the beginning of the entire array. So that's why the offset is 0, and that's why we call it the 0th element, not the first element, because it is at exactly the same place as the entire array itself. And this is the thing about C and C++ is it's C++ and C++ is an extension of C, and C itself is actually very close to assembly language. The origin of C was the two people who wrote Unix. They were writing the operating system in assembly language at the time, and very quickly they realized, that's a lot of work, that's a lot of chore. So they invented, a programming language, the predecessor of C, as kind of a macro language, so that they can write code in a much more efficient way. But that's why C is so close to low-level stuff compared to other programming languages, is because it was a programming language intended for writing parts of an operating system, and you need low-level access when you're doing that. All right, so since you're here, since I still have the attention of a good majority of the class, I'm gonna throw a wrench into this whole thing, and I'm gonna say that I'm using member X as an index to member Y of the same structure. And
Okay.
I have a typo here. Yeah, go ahead. Now, the question
Oh,
is,
just saying, following.
okay, all right, cool. So now the question is, do we know enough of how to deal with this? Okay, and how do we approach this? So let's go ahead and think about this. Okay, so think about it not in assembly language, but in C, and just look at this from the perspective of the C programming language. So in order to figure out where we are supposed to store this 4, now the 4 is not really the big deal, right? Because 4 is just a constant of 4. We can always get to the constant of 4 anytime we want to. Not a big deal. But where we are going to store this is now a little bit more interesting. So I don't even care about y until I know what is var1.x. In other words, I need to know about the index before I know, oh, this is the index of which array. So this is the kind of way that we need to think, is ordering. Okay, so when we are compiling a program, when we're converting a high-level language program into assembly code, what you're trying to do is really resequencing things. Okay, you're sequencing things and go like, okay, what do I need first? Then what do I need? Then what do I need? Then what do I need? It is about sequencing. Unfortunately, the syntax of C and C++ does not always suggest the sequencing when you just look at, oh, I just need to read from left to right. That doesn't work, okay? So you have to think about it and say, okay, eventually we are dealing with indexing here. So that means I don't really need to know which array I'm indexing. I just need to know the index first. So that's the first thing we need to know. Once you figure out the index, then you figure out, oh, which array are we indexing? So that's the order of how things are supposed to be figured out. So now that we understand that, we go back to the assembly code, and now we can update the assembly code to reflect what we have in the C code here. So instead of just kind of hacking the existing program, I'm just going to rewrite that portion entirely. Now, in this case, because the left-hand side is significantly more complex than the right-hand side, I would do the left-hand side first, because it might need all 3 registers that I have to make things kind of convenient. Okay, so the first thing we need to do is to get to var1.x, but we know how to get to var1.x already, because the code right before this is how we got to var1.x. But I'm gonna just go ahead and do that anyway over here. So we have LDI A with var1, add AD. So now we have the address of var1 in register A, and then we say, we don't want the entire var1, we want one member of var1, so we also want to LDI. Now this, okay, I'll go back to the shortcut in just a little bit. So now we need to get the offset to member X of var1 and then add that to register A2. Okay, so I'm going to pause a little bit here and basically say, in this particular case, okay, if you think about what we are adding var1, D, and XX together, right? There are 3 things we are adding. But of the 3 things that we are adding into register A, 2 of those are constants. So that means, we can combine the constants into one single thing and not have to deal with the additional instruction to perform that add to XX. So is that okay? This is a simplification of what we did from before. This is okay in this case because we are starting with an actual structure, and then we are adding the offset to a specific member of that structure. If we are dealing with a pointer to a structure, then we would not be able to simplify like what I just did. All right, so on line 56, we now have the address of member X of var1 in register A. So that is good, but that's not exactly what we want, because we do not want the address of member X of var1. We want the value because we want it to be the index. So that means we need an LDAA. So basically, whenever you use LD or whenever you use ST, whatever is in parentheses is dereferenced. That is the reason why I syntactically make it stand out, okay, putting the parentheses around the register that is being dereferenced. Okay, so now register A has var1.x. The next question is, okay, so we have the index, and we are indexing into an array. Where's the array? Okay, so let's find out where the array is located. So we have the same thing. This time we use register B. var1 is the offset to the structure itself, but of that structure we want to access member Y, so we can now combine the two additions into one. And then we still need to add a BD because we need to get to the actual address. But register B on line 58 is not just the offset to var1, but it is the offset to member Y of var1. But it's still an offset from where the stack pointer is pointing to, and that's why line 60 is needed in order to turn the offset into an actual address. So at this point, we have the beginning of the entire array, that we know as member Y of the structure. We have the index in register A. So now it is just a matter of adding those two. So we have add BA. So the B is now the address of whatever element that X is indexing into. Are we doing okay so far? More or less? Okay.
Yeah.
Okay. And now we only have the right hand side to worry about, right? So the right hand side, we can reuse register A. Okay, there's no need for register A to continue to hold its value, which is really just the value of register, not register. It's register A was the value of member X of var1, but we don't need that anymore. We can just toss it. So now we can just use it to store whatever the right hand side is specifying. And then we have a SDBA, and that's how this part is done. Now, I do want to point out one thing. Yes, there's always something to point out. The fact that we are just adding the index into the base of an entire array, it works in this case because every element only has 1 byte. So if each element has 2 bytes, then you have to multiply A by 2 first. If each element has 4 bytes, then you have to multiply A by 4 first. So we kind of lucked out in this case because we are dealing with each element of Y only has 1 byte, so we don't need to do any multiplication. Is that okay?
All sounds good to me.
Alrighty. So, well, it doesn't hurt to test run this code because I can claim this code works all day long, but in the end, we really need to test it. There we go. And in some way, sometimes I hope my code does not work, so I can actually show you guys how to debug a program, which I think is actually very educational. It really helps you to understand the concepts in a much deeper level when you need to debug a program. And you won't find too many people liking the process of debugging a program. All right, so now what are we expecting, right? Because we need to figure out what we should be expecting in this program before we can look at the trace and go like, yep, it did what it's supposed to. So in this case, we are changing Y bracket 2 because X, member X has had a value of 2 when we index into member Y to change that location. So that means this location needs to get a value of 4 this time. So that would be location 253, which is in hexadecimal FD. Okay, so FD is supposed to get a value of 4. So now we can check that. Jonathan is way ahead of me. All right, so we got the 2, and we confirmed that we got the program worked correctly. Location FD got a value of 4. So there you have it. So if you want to, make another snapshot, and also don't forget to. I'm going to post everything here. So you can take a snapshot of the assembler, and I am going to copy and paste the C code into the text channel. So this way you know what the original C code looks like, and then you get the assembly code. So let me see, where's my GDB? There we go. All right. So in the text channel, I am pasting the C code. All right. So there you have it. There are not too many new topics, Jonathan. So from this point on, it is more or less just how to reapply the same concepts in different ways. Think about Legos, okay? Think about Legos. I introduce, specific pieces of Legos. Some are flat, some are long, some are short, some can rotate, and so on and so forth. Okay, so each Lego piece is now introduced. Um, but there are many, many different ways to reconnect between the Lego pieces so that you can design a car, okay, you can design a boat, you can design a house, you can design a robot arm, and so on and so forth using exactly the same Lego pieces. So at this point, we have all the pieces already. Okay, we know about how to translate from C code into assembly code for just about everything that I want you to understand. Okay, so we got pointers, we got parameters, we got local variables, we got structures, we got local variable. No, I said that already. We got conditional statements, we got loops, we got conditions, we got comparisons, and that's about it. I mean, it's really just about how to recombine those concepts to get something big to work. Exactly. Yep. Well, I'm not sure about that last part, but but that's the idea. Okay, the idea is I'm giving you the pieces. Okay, all of these pieces are already here. It is a matter of how do we connect the pieces, and that is basically looking into. So for everything that we are translating, let me point back to here. So for everything that we are translating, especially something like this, it looks complex, okay? But in the end, we have to do it one step at a time. So it is all about sequencing what needs to be done first, and then what do we do, and then what do we do, and then what do we do. And once we identify those smaller steps in the sequence, each one of those smaller steps should not be super complex or overwhelming. It is just a matter of sequencing the entire thing. So that's going to be what we will be working on Tuesday. I will upload the test again today in the text channel, for the discussion on Tuesday. It's gonna look pretty. It's gonna look pretty ugly, but when we talk about it on Tuesday, hopefully, we will, start to get a sense of, oh, okay, it only looks kind of ugly and complex, but once we try to do things one step at a time, it's gonna be not so complex anymore. So are there any other things I can address, using the screen share mode? I'm still streaming, I believe. I haven't stopped my streaming yet. So everything is still being recorded.
Okay, one more question.
Mm-hmm.
I almost forgot about this one, but I was just reviewing my
Yeah,
notes and questions. Okay.
that's a good idea.
Tuesday's class, you went over the J blank I instructions, and you mentioned that JCI and JLI both help determine whether the minuend or subtrahend is less or greater, but not which one does which. And I was trying to track in Logisim, but that's where I think we get kind of deep into the flags,
Mm-hmm.
and I'm not great with the flags.
Okay. All right. So Okay. So when you look into I'm trying to get to the practice test at the same time, so I'm multitasking. Um,
Okay, and also I really appreciate you. We all do, like a lot.
well, this is not an easy class. I understand that part, and it was not really meant to be. It's not an easy class because because it's not your usual programming. Okay, that's the first thing. It's not the usual programming, and I cannot use the typical way of teaching this class. I did that for a while, and it wasn't working. Okay, people in the end, at the end of the semester, they were not getting the concept that they were supposed to get. So this is not an easy class, and to succeed in this class, is not studying as in just going over the material and make sure that we can remember everything. It is not about remembering, because it's open book and open notes. So there's no need to waste your neurons into just remembering things. It is about making the connections between the concepts. So, and also how deep you're understanding a specific concept. So in the text channel, I have just included the practice test that I'll be going over on next Tuesday. So you can take a look at that. And then for Maddie's question, sorry, I forgot about your question, Maddie. Can you, sorry, can you repeat that question?
No worries. Yeah. Okay, so you're just talking about JLI
Right,
and
right, okay.
yeah.
Right. Okay, so let me. I'm trying to find a tab to where I need to go. Okay, cannot find it. Okay, let's locate it. Yeah, I got way too many tabs open. Okay, I just might need to get there again. Okay, so let me go to, what is it? Apps. There we go. Alright, so getting back to the flags. Okay, the flags they were discussed before the first exam. So let me locate that note first. Alright, so that should be in this particular section. It's a long section. And it is about binary subtraction. So this is binary number addition. Subtraction is right here. And then we have the comparison. So between this binary subtraction module and also the binary number comparison module, the two flags that we ended up using, one is called the borrow flag, the B flag, and the other one is what I call the L flag. So for unsigned comparison, which is this portion of the notes here, okay, there we go. So the bottom line of binary subtraction is B, which is the borrow flag, the overall borrow flag after a subtraction, is a 1 if and only if the minuend is less than the subtrahend for unsigned values. So that's the bottom line. Let me go back to Joplin so that we can just kind of type it in Joplin. It's easier that way. Easier for you guys to see anyway. So comparisons. So the B flag, okay, B flag is a 1 if and only if the minuend is less than the subtrahend unsigned. So that's kind of the conclusion, of the discussion of the flags. And then the L flag is the other one. L flag is 1 if and only if the minuend is less than the subtrahend, but this time it is signed. So that's kind of the bottom line, but we don't have a B flag. There's no JB, or JBI, because in the architecture, B and C are combined into 1. So that means JCI is what we need if you have an unsigned comparison and you want to confirm that the minuend is less than the subtrahend and then branch, and then JLI is the one that we need if you're dealing with signed values. Is that helping?
Yes. And then can you give an example of when in C code, like when in code, we would want to use this?
Okay, so so what you need to do is to look at two different types of comparisons in in C code. So you can look at the first one. Okay, u in 8 underscore t. We have xy, and then we have int 8 underscore t. I'll call these I and j. Okay, so if you want to say if x is less than y, do something, that would be a unsigned comparison. You are confirming that x is less than y unsigned in order to perform this operation here. On the other hand, if you want to say if I is less than j, I want to do something over here, then you're looking for I being less than j in a signed manner. Is that okay?
Yes. Okay. So for the first one, X is less than Y, we would want to use a JCI instruction. And for the
Mm-hmm.
I less than J, we would want to use a JLI instruction, right?
Right. Now you have to be careful because the JCI and the JLI will branch if and only if the C or the L flag is a 1. So in this case, you want to go to the then portion when x is less than y. So that means the assembly code corresponding to this is going to be CMP, assuming x and y are both registers. So you basically would do a compare, which is essentially a subtraction without storing the difference. And then what you need to do is to look at the flags. So in this case, you have no choice but to look at the C flag, and we only have one conditional branch based on the C flag. So we have a JCI. The question is, where are you going to branch to? So you have to branch to the then branch in this case. So you have to basically say JCI go to the then branch, which also means if you do not perform the JCI, it means x is not less than y, in which case you have to go to the end of the conditional statement. So you have to get to the end label in this case, which also means in this case you also need to define a label here. So the then branch is going to be a label definition that marks the beginning of the then branch, and then you also need a and branch or and label defined here so that you have a way to bypass the entire then branch in case x is not less than y.
Okay. Awesome. Thank you.
All right. And Lisa is typing something, so I'm gonna wait a little bit before deciding what to do next. There we go. Oh, okay, not a problem. Not a problem. Yeah, I wish we could do this, that we were able to do this early in the semester. But this is important. I can publish my Joplin for today into a PDF and then share that with all of you. So there we go. How many people are using Joplin or something like that for taking notes? It's not too many people. All right.
I'm old-fashioned. I have paper.
That works too. The important part is people are actually taking notes, because not taking notes for a class like this and then spending time to review the material is going to be very difficult. It's going to be very, very hard. Oh, I forgot to press the enter key, so now the practice test is up online. Tablet works really well too. And I am going to post the PDF of today's Joplin. So we upload a file. There we go. And there we go. Alright, so the Joplin note is uploaded now. Alright. Anything else? Anything else before I stop my screen share? Okay, Notepad as in just Notepad or or the program Notepad? I really like Joplin because Joplin, the program, okay. I really like Joplin because it uses Markdown, and once you get the hang of Markdown, it's very quick and very efficient to type notes, even if you have equations and other things to type into. And you can do screenshots and just paste the screenshot into Joplin too. It handles that really well too. All right, so we are going to go over the practice code on Tuesday, not Tuesday and Thursday, just Tuesday. And then on Thursday, we are going to go over the solution of a homework that I'm going to assign today. I know you guys already have something that's due on Tuesday, but I think it is important to also get some hands-on experience with structures. So I'm going to give you guys a one more assignment that's going to overlap, but that one is the new one's going to do on Thursday. So next Thursday, I'll be giving you the solution to the assignment that I'm assigning today. All right. Any other questions? I like the ampersand. All right. Well, I'm gonna stay online in the text channel, and just in case anyone wants to talk about anything. But other than that, it doesn't seem like we need to continue with the screen share. I'll give you guys a few minutes when I'm oh, right, I need to give you the assignment. So you guys can sign up if you want to. I don't have anything planned at this point, but if you have any additional questions that you want me to address when screen share is still on, go ahead. Oh, yeah, absolutely. Absolutely. I think I teach better when people ask me questions. Yeah, then it's not teaching, right? Then it's just me responding to questions. But I like responding to questions.
I feel like teaching in general is just imparting your knowledge. And so, whether it's you doing that by specifically giving someone information that they asked for, or you just having your own list of what you think it should do, you're teaching.
Well, it's not just knowledge. I think I know this sounds like a pipe dream to some people, but what I really want to teach is to the point where you don't need me anymore. I'm trying to teach you guys out. I'm trying to do my job so that I don't have a job anymore. By the time you guys can learn by yourself and go like, I don't need a teacher to learn something, I think that would be good. Okay, so I'm gonna have to reset all of this stuff here. And this is gonna be in a week. Today is the 2nd, so 1 week would be the 9th. So December 9th at 9 a.m. There we go. All right. Oh, the PDF generates an error. Darn it. All right, so I'm going to regenerate the PDF. All right, so looks like we are good to go without the screen share. I can still talk to you guys individually, or if I need to, I can get back to the voice channel. But right now, I think I can just go ahead and leave the voice channel. All right, so I will regenerate the PDF and post it again. This time I'll double check and make sure it's good, and then we'll go from there. I will be online until 1:20 p.m. as usual. Okay, that's fine. Whenever you guys have any questions, just go ahead and ping me. It might take me a little bit of time to get back, once I'm out of the class time or the office hour, but it might take, but I'll get back to you guys. All right, you guys have a good day. Have a nice rest of the week and a nice weekend. Thank you.